This lecture is called Optimal Design of Water Supply Pipe Systems. We are going to use optimization methods for the optimal design of water supply pipe systems. Before doing that, it is important to understand the basic hydraulic and economic concepts. We are going to give several examples to demonstrate the use of optimization methods. For most of the calculation, except for the last examples, we are going to use spreadsheets for calculation. The first example is about pipe-pump trade-off. It is called the Thurstville problem, taken from the book by Alan Smith. This slide shows the layout where we have a reservoir and we have to transmit water through a pipe and a pump to a city where they have a storage reservoir to accommodate for the difference in demand. If we look at the problem, we can distinguish between 5 different variables: the discharge in the trunk main, the diameter of the trunk main, the head loss in the trunk main, and storage volume in tank and pump horsepower. These variables have interrelations expressed by 3 equations. One of them relates head loss HF to Q, and the second one relates horsepower to discharge and head loss. The third equation is to calculate the volume of the floating reservoir calculated from the demand curve, where we multiply the number of hours where the discharge is greater than Q by 3060 seconds, and then multiply this by 0.6 minus Q, where 0.6 is the maximum discharge. Out of the 5 variables, D, Q, HF, HP, and volume, V, only 2 variables are independent, D and Q. The other 3 variables, which are HF, HP, and V, are dependent and can be calculated from Q and D. The total cost of the system contains the cost of diameter in equation 4, the cost of the reservoir in equation 5, and the cost of the pump in equation 6. The algorithm used is in the exhaustive search. Start by choosing a value for D to calculate the cost of the pipe, and then we choose a Q to calculate head loss and calculate required head loss from both those calculations. We can calculate the cost of the pump. Then from the demand curve we can calculate the required storage volume, from which we can calculate the cost of the reservoir. When we add the cost of the pipe and the cost of pump to the cost of reservoir, we get the total system cost. A long time ago, before the invention of even calculators or computers, this is in the 70s, we used to use charts to solve problems like this. We enter the value of discharge, from which we calculate HF, and using the same value of discharge, we can calculate the cost of the reservoir, and from we choose, and the same time we use Q to calculate the cost of the pump. When we choose a value for the diameter, we can calculate the cost of the pipeline. We add C1 to C2 to C3 to get the total cost of the system. This is a plot of the iso-coastline that shows us the domain of all possible combinations of discharge and diameter. And this particular graph shows that this contour map showed us two minimum. One of them is the local minimum, and the other one is a global minimum with optimal values 0.408 for diameter in meters, and the discharge is 0.35 in cubic meters per second. The total minimum cost is 1,009,068. Now we are going to leave the solution using charts, and we are going to use optimization by enumeration, meaning we test all the feasible combinations of Q and D in the whole domain and choose the minimum one. Now we use a 4-term program. In this 4-term program, we have two nested do loops to try 50 values of Q and 50 values of D, which comes up with 2,500 combinations. For each combination, we calculate the volume of the reservoir, the head loss, the pump head, and then the horsepower, and then we calculate the cost of the pipe, cost of the pump, and cost of the reservoir, and cost of the pump. Every time we do this calculation, we calculate the total cost, and we use this total cost and compare it to the one before, and if it is less than the one before, we replace the value of cost and store the value of the corresponding discharge and D. If we do this 2,500 times, by the end we can print the minimum cost and the optimal values of Q and D. But in this calculation and in the next examples, we are not going to use Fortran, but we are going to use spreadsheets. Spreadsheets are powerful computational tools, and in this particular example, we designed the spreadsheet where these are some selected values for diameter and for discharge, and this is the demand curve from which we calculate the volume of the reservoir, and these are the design calculations shown before where we calculate head loss, horsepower, average flow, and reservoir volume. Cost calculations for C1, C2, C3, and this is the total cost of the system for these selected candidate values for diameter and discharge. But in Excel, if we have a two-dimensional problem, we can use a two-dimensional table by clicking on data and then click on what if analysis, and we use data table. We put all the candidate diameters in the row and all values for flow in the column, and we highlight all this range after copying this value here. And then by doing that, the next step is we choose the two-dimensional table and tell the two-dimensional table where the row input cell comes from, which is B4, and where the column input cell B5, which is this one. If you do that and you click OK, all the combinations and the spreadsheet will be repeated as many times as the number of candidate diameters multiplied by the candidate discharge, and we get this table here where we can see that the minimum cost is 1010, corresponding to a value of pipe diameter 0.4 and flow value of 0.35 cubic meters per second. The optimization model, if we like to transform the previous calculations into a mathematical model, we minimize the cost of pipe, function of diameter, the cost of reservoir as a function of volume, and the cost of pump expressed in terms of the horsepower. And these are the three equations relating the 5 variables together, and we have limits because we cannot have a discharge that is greater than maximum flow, and we cannot have a discharge that is less than the average flow, and the volume of the reservoir has to be a positive value. If we do that, we can ask the same spreadsheet to solve the problem, but this time we are not going to use a two-dimensional table. We are going to use a solver window and use GRG nonlinear programming to solve the problem. We give him the objective function and tell them where are the design variables and the constraints relating to the discharge, the two limits for the discharge. And then we hit solve, then we get the solution. We get a solution less than the solution we got before. Why? Because the values obtained for the optimal solution are not discrete according to availability of diameters in market. But we like to notice that this is the same value we obtained from the iso-cost lines in the first calculation using charts. The nonlinear programming solution, this is the same sheet as the previous slide but a bit enlarged, shows you the value of the objective function and the optimal values of diameter, which is continuous, and the optimal value of discharge. We move now to a different type of problem for irrigation pipe networks, where we have a source of water that pumps water through 10 pipes into 5 terminal nodes using 2 pumps, P1 and P2. We have discharge as variables and also head at terminal nodes, and the only 2 equations describing the hydraulics has to do with calculation of velocity by dividing discharge by the area of pipe. The other equation has to do with the head loss due to friction from the famous Darcy-Weisbach equation. To calculate the head at one of the terminal nodes, for example 5, we say the head at terminal node 5 is the head at the source plus the head of pump 1 plus the head of pump 2 minus the head loss from the source going to the path that takes us to node 5. And we repeat these calculations for the other terminal nodes. We have 5 terminal nodes as we have seen before. Now, these are the mathematical relations showing that the discharge at the terminal nodes 5, 6, 7, 9, and 10 are 4 cubic feet per second. Velocity has to be less than 6 feet per second, and the head at terminal nodes has to be more than 550 foot. The system cost, for some obvious reason, we had linear relations to calculate the cost of pipes and the cost of pumps. If we look here, we designed this spreadsheet to put the input data here, and for input data like the example before, we have one column for the symbol and one column for the values, one column for the units, and because we need to define all the variables, I used the fourth column to define the variables. The first one is pipe friction factor, the second is water source elevation and minimum terminal elevation and maximum velocity. We put the terminal nodes here, and we put the 10 pipes in a table where we have pipe number and we have the diameter that we are going to choose from the list of available diameters in the marked, and this is the length of each pipe, it's constant, and the discharge calculated backwards from the terminal nodes. Each has a discharge of 4 cubic feet per second, calculation of HF, and the cost of pipes, and here is the cost of pumps from the cost table here. They are all linear functions, and we use conditional formatting in Excel through the trial and error design to warn us when the value is colored, it means it violates the constraint. As here at node 9 and node 10, the terminal node constraint is violated, and for the velocity at pipes 1, 2, and 3 and 8, the velocity constraint is violated. Now, after the trial and error method, we used a nonlinear programming model to solve using the solver and use the GRG nonlinear again, and we have a starting point. This starting point is the same as the one I showed you before for the trial and error method, and this is an infeasible starting point, but when you ask the computer to solve for the optimization problem, we get a solution. The total cost is 51,057, and the values of diameters are all fractional. Therefore, this optimal solution is not practical because we have to round the diameters into the available pipe diameter in the market, and this is the solution enlarged. Therefore, we have a discretization problem. This rounding procedure is called discretization. And how can we do that discretization? We have two options: either go to the next upper discrete value or the next lower discrete value. This is one of the choices, and we get, of course, a total cost which is higher than the cost of the nonlinear model. The same thing goes for also the value of the head of pumps. But there is a hydraulic trick that we can use, so we obtain a global optimal solution, because the discretized solution, we cannot guarantee that it is optimal. Therefore, we do this little mathematical trick. Instead of using the highly nonlinear variable diameter, we used the length, the length of the candidate diameters. We divide every pipe into 3 portions, and instead of using diameters as variables, we use the length of each of the 3 pipe lengths as variables, so that the HF becomes a linear function, where S is calculated from this equation. Therefore, if we look here, instead of having, we choose 3 candidate diameters, and these candidate diameters, of course, should satisfy the velocity constraints, and we make our variables L1, L2, and L3. Why we benefit from this solution? Because we are going to get now a linear program, and linear program actually has a global optimal solution, and it can handle very huge problems with too many variables and too many constraints. The linear programming model is shown here. We replaced the 10 values of diameters by 30 values of lengths. This 1000 I put as a starting point, even though for linear programming we don't need a starting point. Therefore, this is the objective function, which is the total cost of pipes and pumps, and it's a minimization problem, and the variables are these lengths and these pump heads, and the constraints has to do with velocity and terminal nodes, as we did before, in addition to a new constraint that make sure that L1 plus L2 plus L3 for every pipe has to be 3,000 feet. Now we go to this solver solution where we solve the linear programming model, and these are the optimal values of the candidate lengths, pipe lengths. You can notice here that most of the pipes we keep the 3,000 and we use one of the 3 diameters. But in other pipes we use 2 diameters with 2 candidate diameter lengths equal to 3,000 feet. This is the linear programming solution enlarged. Again, look here, this solution obtained is less than the discretized solution, and of course larger than the continuous nonlinear solution. And this is a comparison between the 4 different solutions that we had, the trial and error, which was infeasible, and this is the total cost for the nonlinear program, and the total cost after discretization, and this is the cost of the linear program. And this is, we described the solutions as infeasible, optimal continuous, optimal discretized, and optimal. Water distribution network, another type of networks where we have a more complicated network with 2 reservoirs and 8 pipes, with also pumps and pressure reducing valves and other types of valves or fittings. For this particular problem that is a bit complicated, this is a mathematical model where we have to minimize the cost of pipes, diameters, and valves, pumps and valves. We have a constraint for the loop equations and a constraint for the head at nodes, and we have a set of equations for continuity and a set of bounds or limits on variables where diameters, discharge, and shut-off heads of pumps have to be between a minimum and a maximum value. Similar hydraulic relations, of course, like previously stated, relates head loss to length and diameter, and the minor losses is related to the velocity head, and the head of the pump is calculated from an equation using discharge, 2 constants, and the value of the shutoff head of the pump. To do this sophisticated nonlinear programming model, we have to define the network. I designed the standard data where we have 5 records. The first record is the description of the network in terms of number of nodes, links, sources or reservoirs, pumps, pressure reducing valve, and constrained nodes. The second record is some constants like acceleration of gravity, coefficients for pump characteristics curves, the C1 and C2, and description of nodes, where we state the node number, the external flow, the minimum head, and if the node is constrained or not. The third record describes the links in terms of origin destination or upstream, downstream node numbers, length, diameter, Hazen-Williams coefficient, the flow, the shutoff head of the pump, and then the constants of the minor losses and the pressure reducing valves. The last record is values for bounds or limits for D minimum, D maximum, Q minimum, Q maximum, H naught minimum, and H naught maximum. And this is the standard data. From the standard data, we use a non-linear programming model using package called Minus. Actually, it's the same package that is used in Excel, but at that time, when I did this example, the spreadsheets were not available. It was early 80s. This is the starting point. For nonlinear optimization, we have to have a starting point. But the starting point has this value of cost, 36,661. Using this starting point, the optimization model solves for a continuous solution where the values of diameters are not discrete. And the value we obtained is much less the previous one, which is 24,516. We go to the discretization problem. This is a bit complex. Why? Because there are two solutions to the problem. Either a direct solution, but using a completely different optimization methods like dynamic programming or mixed integer programming, or we use indirect solution by rounding the variables. And this can happen for linear programming and nonlinear programming. But we have to warn you here that solutions obtained should not violate the hydraulic constraints. But to make our life easy, we can make some of these constraints soft constraints, and we can allow some violation to facilitate the procedure that we are going to explain very soon. This is an interesting ISO coastline that warns us that if this is the continuous solution, the discrete solution can be thought as one of those four solutions. But because of the nature of the cost function, the discrete solution is away here. Therefore, this is to show you that in nonlinear problems, you cannot guarantee, even after the discretization procedures that we are going to explain, that the obtained solution is the lowest one. And it's called the banana function. Here we are going to use a simple discretization problem by using a network of two pipes, link 1 and link 2. Each pipe has different lengths, different Hazen-Williams coefficient, and different discharge, where the upper link has 6 cubic foot per second and the lower link has 4 cubic feet per second. If you look here, we have to look at the 4 discrete neighboring values. But by looking at the next lower and next upper diameters for link 1, and for this next lower, we have for link 2 to test next lower and next upper. Therefore, this sketch here showed you this is a continuous solution, and these are the 4 neighboring discrete solutions obtained from this lower row of the tree shown. But I myself, to make my life easy, I came up with a simple way to do the discretization, and I called it the cost-based solution, where I dealt with every link separately to decide which of the two nearest discrete values are more economical. Diameter and shutoff head modification should be able to produce a feasible solution. Why? Because I play with the shutoff head of the pump and the diameter to satisfy the constraint. And the optimal solution may be found at the expense of perturbing the energy and nodal constraints in the vicinity of the links, as I mentioned before. Therefore, these two total energy line sketches shows you what happens if I use the lower discrete and upper discrete to the total energy line for pipes that don't have pumps. But in this, if I use a lower discrete value, I need to use a pump. At least I assume that, and calculate the cost as if there is a hypothetical pump here to allow me to satisfy the constraint at the downstream pump. But for pipes with pumps, I don't need to have a hypothetical pump. It is really there. And this is what happened to the total energy line. This is a continuous solution, and this is a lower discrete one and the upper discrete one. I use this illustrative example, which is different from the example I used before to solve the nonlinear optimization model. And I used the example I showed you before, but because the results are shown in SI units, I did this conversion table so that when you see the results of the model in the following slides, you know that it is expressed in cubic meters per second and meter. And this is what I get. This is a continuous solution where you can find the diameters here are all continuous, and these are the actual head at nodes, and of course, and this is the required head at nodes, where each actual should be greater than or equal h required for all nodes to obtain a feasible optimal continuous solution. Therefore, I used the cost-based analysis I described in the previous slides to handle each pipe individually by choosing the discrete value, the lower and the upper discrete value, and calculate the change in the cost of pipe, the changes cost of pump, and the decision. NA means there is no saving. If there is no saving, I will use the lowest of these two numbers. Here, the decision, I saved this money, therefore that pipe is reduced. Here, there is no reduction or increase, therefore I used the least difference. I use this one. And here, when I increase the diameter, I save this amount of money, therefore the decision is increased. Here the decision is reduced. Here I will use this one, and here I will use this one. If I use this pipe diameters, the discrete ones after this cost-based analysis, I get this thing. As you can see, I get the diameter. These are from the previous table, the optimal discrete values, and of course the total cost of the network will be higher than the continuous solution for obvious reasons. This is the last slide where we went through a series of slides that shows us the optimization methods and how powerful they are for optimal design of water and irrigation systems. In order to have the solutions required, we have to have basic knowledge of the hydraulics and economic concepts. And we used spreadsheets for most of the examples except for the last one as efficient calculation environment to get the optimal solution for the first problem, the Thurstville, and the other one which has to do with the irrigation systems.